As I mentioned earlier, today's agenda is on advanced signal processing algorithms other than FFT. Many sound and vibration applications have adopted signal processing. FFT-based signal processing algorithms, for example, power spectrum and total harmonic distortion measurements, are the most widely used. However, FFT-based signal processing algorithms might not help in some applications. This presentation will introduce several advanced signal processing algorithms beyond FFT. These advanced signal processing algorithms can solve some sound and vibration challenges that FFT-based algorithms cannot solve. This presentation will introduce the background of these algorithms and their applications examples such as bearing fault detection, dashboard motor testing, and speaker testing. Sound and vibration signals can indicate the condition or quality of machines and devices. Many machines and devices generate noise or vibration when they operate. You can analyze sound and vibration signals when you design and manufacture a product. You can also analyze sound and vibration signals to monitor the conditions of critical machines in their working state as well as the structure. For example, when a cooling fan spins, it generates noise. High-quality cooling fans produce lower levels of noise. Defective cooling fans, for example ones with bearing defect or broken blade, produce higher levels of noise. Before you select the right algorithm, you need to understand the characteristics of the signals first. If we look at the signal characteristics in the time frequency plane, we can understand the signal characteristics better. Some features have a long time duration but narrow bandwidth. For example, rub band buzz noise. Some features have a short time duration but wide bandwidth. For example, spikes and breakdown points. Some features have a short time duration and narrow bandwidth. For example, decay resonance. Some features might have a time varying bandwidth. For example, the imbalance bearing generating noise dependent on RPM. You might need to use different signal processing algorithms for different types of signal characteristics in the time frequency plane. There are many signal processing algorithms that you can use to extract signal features. Based on the independent variables in the algorithms, they can be classified into time domain, frequency domain, time frequency domain, Quefrency domain, Wavelet, and AR model based. We'll focus on time frequency analysis, Cepstrum, Wavelet, and model based algorithms in this presentation. There are many algorithms that you can use, so the question is how to select a correct algorithm. We'll look at each algorithm and see their fit in this table. So what we see in this table is on the x-axis you have different algorithms or the types of algorithms that are offered in LabVIEW, and and on the y-axis we have types of signals. So based on the types of signals we will select which algorithm is the most suitable in that particular measurement. Frequency analysis is inherently suitable for analyzing signals with narrow band or harmonic frequency components that do not change over time. Order analysis is suitable for analyzing time-varying signals that are dependent on RPM of rotational machines. We will present the fundamentals of other analysis algorithms and see where they fit. Before we talk about time frequency analysis, let's look at the frequency analysis first. Frequency analysis is the most commonly used analysis method and it is very useful in many applications. The FFT is the basic operation in frequency analysis. Frequency analysis results such as power spectrum and TSD contain only frequency informations of the signal. These results do not contain the time information. Frequency analysis are useful for analyzing stationary signals whose frequency components do not change over time. For short time duration signal components, frequency analysis might not be useful because the short time duration signal components might have low power and be drowned into the spectrum of noise. The simple example is to compute a linear chirp at its time reversed version. While frequencies of one chirp signal increase with time on the top left, frequencies of the other chirp signal decrease with time on the bottom left. Although the frequency behavior of the two signals is obviously different, their frequency spectra, which on the right computed by the FFT algorithm, are identical. As a matter of fact, there is an infinite number of completely different signals that can produce the same spectrum. So it becomes important to analyze different signals in different way in order to analyze or characterize their properties separately. Transients have sudden events that last for a short time. They usually have low energy and wide frequency band. When they are transformed into frequency domain, their energy will spread over a wide range in the frequency domain. Since they have low energy, you might not be able to recognize their existence in the frequency domain. The time frequency analysis results are usually given in a spectrogram. A spectrogram shows how the energy of a signal is distributed in the time frequency domain. A spectrogram is an intensity graph with two independent variables, time and frequency. The x-axis is time and the y-axis is frequency. The color intensity shows the power of the signal at the corresponding time and frequency. A chirp pattern is a signal whose frequency linearly increases over time. From the power spectrum of the chirp pattern, you can only see the frequency components of the signal, which are from 100 Hz to 400 Hz. However, the spectrograph shows how the frequency of the chirp pattern changes over time. You can see that the frequency increases from 100 Hz to 400 Hz in 1 second. Time frequency analysis represents a signal in the time frequency domain. These results reveal how the frequency components of a signal change over time. Time frequency analysis is suitable for analyzing time varying signals. So this is how two different chirp signals are characterized using the time frequency analysis indicators. Time frequency analysis can be used in production testing. Here is an example in speaker production test. In production testing, speakers play a long chirp. Operators listen to the speakers and judge the quality of the speakers. A long chirp is a time varying signal whose frequency changes from 10 Hz to 20 kHz. You can use time frequency analysis algorithms to analyze the sound generated by a speaker to judge the quality of the speaker. The spectrograph of a signal is very clean. You can see the good speaker generates the expected frequency components, except there are harmonics which are acceptable if the harmonics are not that high. Conversely, the spectrogram of the failed speaker contains many abnormal components. You can see on the screen on the right hand side bottom the graph or the spectrogram of a failed speaker contains many unexpected components on the left hand side as compared to the spectrograph of a good speaker. This table is a rule of thumb in selecting the right algorithm based on the time frequency characteristics. Note that these are guidelines only. If the signal is narrow band signal that lasts for a long time, use frequency analysis. If the signal contains harmonics and lasts for a long time, use Quefrency analysis. We'll come to Quefrency analysis in short time. If the signal is time varying, use time frequency analysis. Next topic is Quefrency analysis. The word Cepstrum was derived from spectrum by reversing the first 4 letters of the word spectrum. A cepstrum is the inverse FFT of the log of spectrum. The independent variable of power spectrum is frequency. Correspondingly, the independent variable of cepstrum is called Quefrency. The name of Quefrency was derived from frequency by reversing the first 3 letters and the second 3 letters of the word frequency. Quefrency is a measure of time, but it is not in the sense of time domain. A spectrum reveals the periodicity of a time domain signal, while a cepstrum reveals the periodicity of spectrum. You can consider cepstrum as the spectrum of spectrum. Another property of cepstrum is that it can reveal the periodicity of a spectrum. Spectra are the easiest tools to use to understand the periodicity of a signal. So a cepstrum is also called a spectrum of spectrum. Harmonics are very common in spectra. Harmonics are periodic components in a spectrum. So we can use a cepstrum to detect whether there are harmonics in a spectrum. One of the applications is bearing fault detection. So you can see on the graph that there are 10 Hz harmonics on the left hand side in the power spectrum. So this 10 Hz harmonics is detected as Quefrency, the Cepstrum analysis of the power spectrum. And the harmonics which are called, or the quantities which are quantified as harmonics in power spectrum are quantified as Rahmonics in Cepstrum or Quefrency analysis. You can see on the left hand side in power spectrum we have two harmonics present, one on 10 Hz and the other one is at 13 Hz. So when we see the harmonics of these harmonics, we see that there is one harmonic present on 1 by 13th, which is 0.087 second, and the other harmonic is present on 1 by 10th, which is equal to 0.1 second. Here are the highlights of Cepstrum analysis. Cepstrum analysis is good for deconvolution. Applications include RPM detection and echo detection. It is also good for detecting harmonics. The next analysis that we'll be talking about today is wavelet analysis. Wavelets are defined as signals with two properties, admissibility and regularity. Admissibility means that wavelets must have a bandpass-like spectrum. Admissibility also means that wavelets must have a zero average in the time domain. A zero average implies that wavelets must be oscillatory. Regularity states that the wavelets have some smoothness and concentration in both the time and frequency domains. So wavelets are oscillatory and compact signals. As a comparison, sine waves oscillate along the time axis forever without any decay, which means that they are not compact. So sine waves do not have any concentration in the time domain. On the other hand, sine waves have extreme concentration in the frequency domain, which is a delta. Sine waves have maximum resolution in frequency domain but have no resolution in time domain. For example, if I shift a sine wave with its periods, you cannot realize I have shifted it at all. Wavelets have limited bandwidth in the frequency domain and compact bandwidth in the time domain. So wavelets have a good concentration and resolution trade-off between time and frequency domain. Here you can see that on the left hand side we have three time domain signals, and on the right hand side we have the spectrum of these three time domain signals. So the signal with high time bandwidth on the left hand side has got the lowest bandwidth in the frequency domain on the right hand side. Here is just a comparison of three different wavelets. Let's have a look at the FFTs of different time domain signals. Now let's have a look at the wavelet transforms of different wavelet signals. A wavelet transform has adaptive time frequency resolution, which means that the frequency or time resolution adapts to the frequencies which exist in a given frequency domain or in a given time domain signal. Here is an example that uses wavelet analysis in the production test of a dashboard motor. A dashboard motor is a stepper motor that has an angle constraint. Instead of rotating in 360 degree, there is a dead zone. It can only rotate between two angles. Oil meters, tachometers and speedometers on an instrument panel all use this kind of a motor. This production test is mainly designed to detect two kinds of faults in a dashboard motor: knocks at turning angles and drop when rotating. Listening to the signal of faulty motor 1, you can hear da-da sound. which are knocks at a turning angles. The faulty motor 2 has more obvious knocks. In addition, the faulty motor 2 has rub noise which sounds like ZZ. As a comparison, there are no Dada or ZZ sounds in the signals of a good motor. Let us now hear to these sounds first. I'm playing a good motor sound now. I'll play the sound of the motor with knocks. And now is the sound of the motor with larger knocks and rub. You can use a wavelet transform to detect the knobs and rubs in the signal. From the wavelet result plots, you can see the knocks results in greater wavelet coefficients. Rubs also result in relatively greater wavelet coefficients. The wavelet coefficients for a good motor are smaller when compared to those of the faulty motor. Why do the knocks and rubs result in greater wavelet coefficients? If you zoom in on the signal to see the details when knocks occur, you will see knocks are spikes and resonance in the signal. Spikes and resonances are relatively high frequency components. If you use a wavelet that has similar bandwidth with these signal components, you will get large wavelet coefficients. You also can understand it as a pattern matching problem. If a signal segment matches a wavelet, that segment gets a high score or high wavelet coefficient. Similar to knock, rub generates high frequency resonance which results in larger wavelet coefficients. Here are the highlights of wavelet analysis. Wavelet analysis is good for transient signal detection. Signals like spikes, edges, breakpoints, peaks or valleys can be detected using wavelet analysis. Multi-resolution analysis can also be done using wavelet analysis. It is easy to find signal events in different scale, for example both wide peaks and narrow peaks using wavelet analysis. Next topic is model-based analysis. You can consider a signal as the deterministic part plus the stochastic part. The deterministic part can be represented by a linear model, while the stochastic part is random and cannot be represented by a linear model. Auto-regressive modeling is a commonly used model. An AR model represents any sample in a time series as a linear combination of the past samples in the same time series. The white noise in the time series cannot be picked up by the linear combination. The modeling error corresponds to the noise that cannot be picked up by linear combination. The AR model spectrum has higher resolution than FFT based spectrum. As you can see on the graph, in the power spectrum of AR model and in the FFT based power spectrum, the resolution is higher in case of AR model based power spectrum. If there are transients in a signal, there might be transients in the modeling error. As shown in the example in the slide, there is a spike in the sine wave. Because the majority of the signal is a sine wave, AR can represent the sine wave as well, but AR model cannot pick up the spike and the white noise. So the spike will be part of the AR modeling error. Here is an example that uses AR modeling to detect hard disk drive faults. You can listen to the sounds of the hard disks. From the sounds of the faulty hard disks, you can hear obvious transients like pitches, cracks, and Z. The AR modeling error indicates the transients clearly. Let me play these sounds one by one. Another application example of AR modeling is engine knock detection. In a gasoline engine, spark plugs ignite to burn the mixture of air and fuel. The timing of ignition is very important and will affect the efficiency and fuel economy of the engine. If the ignition is optimized, the mixture burns smoothly from the point of ignition to the cylinder walls. If the ignition is late, the mixture might be automatically ignited when the temperature of the mixture exceeds a critical value. This auto-ignition produces a shock wave that generates a rapid increase in cylinder pressure. When auto-ignition occurs, the engine might make a knocking noise. From the signal aspect, the signal samples are very different from others when engine knocks occur. Knocks produce transients in the signal, so it is possible to detect engine knocks by using AR modeling. If you listen to the vibration signal of the engine, you can hear 5 knocks clearly. However, you cannot see it from the vibration signal. If you apply an AR model for the signal, you can clearly see these 5 peaks in the AR modeling error. This is a similar example with different data samples. The difference is that this engine was run up and down. If the RPM changes smoothly and not that fast, you can still apply the AR modeling method to detect the engine knocks. So here are the highlights of AR modeling. AR modeling is a good mathematical description of stationary signal. The AR modeling error indicates transients in the signal. Now, this is a table that will now clearly signify all the uses and applications, or where you should use what kind of method. If the signal is a narrow band signal that lasts for a long time, you should use frequency analysis. If the signal contains harmonics and lasts for a long time, use Quefrency analysis. If the signal is a wideband signal and lasts for a very short time, use wavelet analysis or AR modeling. If the signal is time varying, use time frequency analysis. If the signal is a narrow band signal and lasts for a short time, use wavelet analysis. Based on this discussion, here is the contest of the week. Create a VI to acquire sound using a microphone and process it further in such a way that it will identify alphabets or words or sounds and display them on the front panel. You may tune the VI for a particular person's voice and post a video of demonstration online. Also post the VI so that the block diagrams can also be analyzed by us. In order to do this, you may want to record a few words or a few alphabets in your own voice. Then you can use this recorded signal. You can acquire the recorded signal in LabVIEW, and you can use the time frequency analysis or Quefrency analysis or Wavelet analysis or FFT analysis or any kind of analysis that you can think of in LabVIEW to identify the sound or the tone of the words when you say them. Let us say for a word or for an alphabet A, there will be a typical type of signal, or I would say in this case a typical wavelet that will identify the alphabet A. Similarly, you can have the same identification procedure for other words or alphabets, and you can have a pre-recorded signal with which you can compare these. After the comparison, you can display whether the comparison was successful or not, and based on that, you can display those results on the front panel. I hope the problem statement was clear. If there is any clarification required in the problem statement, feel free to ask us on the LabVIEW enabled community. You can go to the LabVIEW enabled community by typing www.labviewenabled.in in your address bar of your internet browser. Extend your Webcast Wednesday learning experience on LabVIEW enabled, the NI India online community. LabVIEW enabled, the NI India online community is a single network of students, industry professionals, and academicians collaborating and coming together to create discussions, exchange and share resources, generate content on applications, NI technologies, as well as the industry trends and other third-party technologies. It serves to unite users not only from India but also across the world on collaborating on similar applications. Simply put, it's a social network for engineers, students, and researchers. Apart from the live online interaction during a webcast, an extended discussion and content on the topic will be carried out for an entire week by the presenter on LabVIEW enabled. Watch the previous episodes of LabVIEW of Webcast Wednesday, get your queries from sessions and LabVIEW resolved, and participate in weekly contents to win up to 50% discount on National Instruments certification examinations. You can attend 20 sessions to win a free CLAD attempt. You can watch the recording of this session and participation in the contest of the week. Here is how you can visit the contest of the week. Just open the website www.labviewenabled.in and click on the Webcast Wednesday graphic you see as you on the page. Thank you for attending Webcast Wednesday. I hope it helped you.